Welcome back to the deep dive. Today, we're taking a scalpel to something truly fundamental in computer science.
Really fundamental.
We're going to the absolute bare metal of computation. We are diving into the world of a theoretical language called MiniPy. And if you thought your latest coding deadline was restrictive, you wait until you hear the rules of this system.
Oh, yeah.
It is a brutal exercise in theoretical minimalism.
It really is. It strips away every single comfort blanket that modern programmers rely on.
Everything.
Forget Python, forget Java, forget even assembly language as you probably know it. This is computation reduced to its core, to its irreducible elements.
That's a great way to put it.
It's like being handed a block of granite and being told to build a skyscraper using only, I don't know, a spoon and a profound understanding of applied mathematics.
That perfectly captures the feeling of working within these constraints. And our mission today is not just to summarize what MiniPy is. We want to analyze the sheer ingenuity and the conceptual cleverness required to perform what we consider to be basic operations. Things you don't even think about.
Exactly. Like multiplication, subtraction, and especially complex iteration, when you are limited to the most basic building blocks possible.
Then when we say basic, we mean basic. We are talking about only 3 core operations. The simplest increment, x plus equals 1, the simplest decrement, x equals 1, and the while loop. That's essentially it for control and modification.
And we have to stress this, we are only working with natural numbers. No negative numbers are allowed in the memory state.
Right.
That constraint alone changes everything we think we understand about arithmetic, especially subtraction.
That's the first layer of limitation. But here's the true foundational constraint, the one that defines this whole system and forces all the ingenuity we are about to discuss.
The big one.
MiniPy has absolutely no stack.
No stack. That means no true function calls, no passing of parameters, and crucially, no automatic memory for saving and restoring context.
None.
If you write a line of code, it affects the memory globally. If you need to save a variable, you have to manually copy it somewhere safe yourself. That absence of the stack is what forces the most elegant yet, the most painstaking programming solutions. If we connect this to the bigger picture, MiniPy functions almost as a foundational model for computability.
Like a Turing machine.
Exactly, akin to a simplified theoretical Turing machine or the core logic of register machines. What's fascinating here is how the limitations of the machine define the elegance of the logic.
So the constraints force creativity.
Precisely. It's essentially assembly language logic applied to theoretical math, and it pushes us to the absolute limit of what the hardware can do.
Okay, let's unpack this world of constraints first, starting with how we even define what a program is in this environment. So when we talk about a program running in MiniPy, we're really defining its state at any given moment. The sources refer to this snapshot as a zustand, a state. What defines that state in this incredibly simple theoretical environment?
Well, the state is defined by only 2 components, which I think really highlights the beauty of its minimalist design. First, you have the remaining program statement, which we can call $7. This is just the sequence of code instructions that have yet to be executed.
The to-do list for the program.
Exactly. And second, you have the memory, or sigma.
Sigma, the memory. In a modern context, that implies gigabytes of RAM and complex pointers. But here, the memory must be profoundly simple.
Oh, it's incredibly straightforward. The memory sigma is a simple assignment map. You can think of it as a variable binding environment. It just says, for every variable currently in scope, what natural number value it holds.
So just variable A is 5, variable B is 10. That's it.
That's it. No complex data types, no structures, just a direct mapping from a variable name to a single non-negative integer.
And once we define the state, then we can define the actual execution. The sources use this concept of Kleinschritt semantic.
Small step semantics.
Small step semantics, right. Represented by that single arrow transition. It feels like watching the program execute one tiny instruction at a time, just moving sequentially from one state to the next.
Precisely. The small step transition, that little arrow, it defines the actual rules of the language. How does the state change?
Right.
The rules for assignments, or Zuazingen, are simple. They just update the memory sigma.
Right.
And if statements, they change the control flow by picking one path based on a condition.
But the crucial element, the real engine of MiniPy, has to be the while loop.
Oh, for sure.
But even the while loop isn't some complex structure. It's explained as basically syntactic sugar for a much simpler branching and repetition mechanism.
That's right. A while loop is simply a condensed way of saying Check the condition. If it's true, run the body. When the body's done, unconditionally jump back to the beginning and check the condition again.
It's the only way to get repetition.
The only way. And paradoxically, it's the element that introduces the language's most profound theoretical limitation.
Which brings us directly to the theoretical problem of totality. We're told that a MiniPy program calculates a partial function. Let's call it $5 in dollars. Can you explain what a partial function means in this context and why it's such a critical idea in theoretical computer science?
Yeah, this is the crucial concept. MiniPy does not guarantee that every valid input will actually produce an output.
Okay.
A total function is one where every single input in its domain maps to a clear output. A partial function, on the other hand, is one where some inputs might map to an output, but for others, the function is simply undefined.
And the reason for this undefined state is the program failing to halt. It just keeps running.
Exactly. The non-guarantee of halting means the function is partial. And the clearest example of this failure to halt, the infinite loop trap, is brutally simple in MiniPy, and something every programmer here has to consider.
Give us that concrete example again, just so we can really internalize the danger.
The example is simple. While x equals 0, x plus 1.
Okay.
So if $6 starts as a positive number, let's say $6 won $1. Is the condition true?
Yes, 1 is not 0.
So we execute the body, x plus in 1. Now 6 equals 1, 2. Is the condition still true?
Still true, and it's never going to be false.
It will never decrease, so it will never reach 0. The program is now executing forever. I mean, it consumes resources until the physical machine fails, but theoretically, it just never terminates.
And theoretically speaking, what happens to that mathematical function at $dollars when it occurs?
If we connect this to the bigger picture, this failure to halt means the mathematical function is simply undefined for that input.
So it's not a crash.
It doesn't mean the program crashed, no. It means the mathematical mapping from the input state to an output state it doesn't exist for that specific input value of $6. This concept that not all programs terminate is central to theoretical CS,
Right.
and it's the core difficulty of the famous halting problem.
Right.
If you can write a program, you have to accept the possibility that it might never finish.
So if we, as MiniPy programmers, want to prove that our program is totally correct, we need two rigorous separate proofs, because the language itself offers no safety net, no guarantee of termination.
That's right. The sources break this down into two essential tools. First, you need partial correctness.
Okay.
This is the easier part, usually. Assuming the program does halt, we have to prove the final memory state sigma holds of the correct result.
And this is usually done with loop invariants.
Typically, yes. A loop invariant is just a statement, a mathematical claim that remains true across every single iteration of the loop. If you could prove that, you prove the logic holds no matter how many times the loop runs.
Okay, but partial correctness isn't enough.
Not at all. The program could run forever, and while it would technically never deliver a wrong result, it also never delivers a right one either.
Which means we need the second and often harder proof, termination.
Yes. We have to find a measure, usually a function that maps the program variables to a natural number, that we can prove decreases strictly by at least 1 in every single loop iteration.
And because we only use natural number, non-negative integers, it can't decrease forever.
Exactly. Since those integers cannot go below 0, the loop must eventually end.
And the combination of partial correctness and termination, that gets us to total correctness.
That's the gold standard for reliable computation. And given that we have to do all this juggling and ensure termination without the luxury of a stack, let's see how they tackle the first major non-trivial operation.
Right, because proving termination requires that our counting measure decreases. So let's see how that simple rule immediately breaks an operation as common as multiplication, and how the MiniPy programmer is forced into some serious manual resource management. Okay, let's dive into the core implementation challenge here. Multiplication, $6 y dollars.
Good.
In high-level terms, this is just repeated addition. We would use nested loops. The outer loop runs though times, and inside that, an inner loop adds $6 to our result variable. Let's call it trial.
The conceptual logic is perfectly fine. The mechanical problem, however, is it's devastating in MiniPy.
Why?
In MiniPy, to count how many times we're adding something, we have to use the only termination mechanism available.
Well, incrementing the counter.
Exactly. We have to decrement the input variable $6 itself.
So the inner loop would be something like while x equals 0, and every time we execute the body, we have to do x equal 1 to ensure the loop terminates, and we can prove total correctness.
Precisely. But if we do that, We have fundamentally destroyed the value of $6.
Oh.
So when the outer loop wants to start its next iteration, 6 is now 0. The outer loop is supposed to run 6 times, but now 6 is gone. We can't add 6 to just again, and we can't even run the inner loop more than once.
This is the critical juncture. This is where the constraint forces ingenuity. We can't destroy the data we still need for future iterations.
Right.
And the solution, this mini pie trick, requires manually saving and restoring the value of $6 using a temporary variable. Let's call it 2.
It's often analogized as the jungler or pouring water between buckets. You are creating a parallel counter that mimics the value of $6 as being consumed. This is resource management, storage, and context saving at its absolute minimum.
Let's walk through the step-by-step logic of this non-destructive multiplication. Let's say we're computing $5, $3 So $6 is 5 and it's $3. Our result $3 and our temporary variable 2 both start at 0.
Okay, step 1. The outer loop begins, controlled by YLAS. Since YLAS is 3, the block of code inside is going to execute 3 times.
And now we enter the inner loop.
We enter the inner loop, which runs while x equals 0. We're going to execute the addition and saving process $6, in this case 5 times.
And this is where the concurrent actions happen. There are 3 lines of code that have to run inside this inner loop.
That's right. Inside this loop, for $6, first we add 1 to the result, $3, to do this 5 times. Second, we decrease $6 to count down and ensure termination, x equals 1. This is the destructive step where $6 goes from 5 down to 0.
And the third step?
Simultaneously, we increase the temporary variable t. So we run t plus equals 1. As 6 goes from 5 down to 0, 2 tall goes from 0 up to 5.
Wait, let's pause right there. This is the absolute genius part.
It is.
$6 is being used for counting. It's being consumed. But $2 is tracking exactly how much of $6 was consumed. So storing the count, which just happens to be the original value of $6.
Precisely. Lure is tracking the decrements. When that inner loop finally finishes, $6 is 0. And we've added $6 to our result exactly once. But now holds the original value of $6, which was 5.
So now the restoration phase begins. The outer loop hasn't finished its first pass yet, but the inner one is done. We have to restore $6 so it can be used again in the next outer iteration.
We exit that first loop and immediately run a restoration loop, something like while t is 0, t always 1, x plus ed 1.
Ah, so you're just reversing the process.
Exactly. This loop uses the value stored in TED, which is 5, to rebuild $6 back up to 5. We are effectively copying the value from $2 back into 6.
And once that's done?
Once it's 0, $6 is restored to 5 and is back to 0, ready for the next iteration. And then finally, we decrement the outer counter dollar from 3 to 2, and we start the entire process all over again.
I have to say, it sounds exhausting just to write what would be 2 lines of code in a normal language. Here you need 10 lines and 3 variables just to do a non-destructive addition.
It's true.
But this manually managed temporary variable dollars is essentially acting as a miniature one-level stack, all manually managed to save and restore context.
It is the ultimate demonstration of minimal resource management. You have to be the memory manager yourself.
And this whole algorithm, as complex as the execution seems, it has to be provably correct, right? Which brings us back to those theoretical pillars from Section 1. How do we apply the proof strategy here?
We have to prove total correctness. So let's start with partial correctness using a specific loop invariant. We need to define a property that holds true before the outer loop starts and after every single iteration.
What would that be?
Well, for multiplication roller, XXIO, a strong invariant needs to relate the final result, $3, to the original input values. Let's call them XIA and on 2 words. We want the final result to be GRIDARO and Illustramat.
Okay, but inside the loop, Yeller is decreasing, $6 is getting destroyed and then restored, and Thriller is increasing. The actual values are constantly in flux.
That's why we need a clever invariant. The invariant for the outer loop has to state that the total desired product is somehow maintained across all the variables. A standard one would be something like the amount already accumulated in $3 plus the product of the remaining $6 and Yeller must always equal the original total product.
So let's try that. If we restore $6 perfectly every time.
Then we can say that after taller outer iterations, our result, Troilers, will be equal to times the original value of $6. And at the same time, they will be equal to the original Yael minus $.
That seems to hold up.
We also have to prove that the inner loop, the one that does the restoration, doesn't violate this. And the inner loop's invariant is simpler. The sum of $6 plus D must remain constant throughout its execution. That proves the quantity is preserved.
So if we can prove that those invariants hold, that the desired mathematical relationship between the variables is preserved, then we have proven partial correctness.
Exactly. And the termination proof is much cleaner here.
Because of dollars.
Right. The outer loop is guaranteed to terminate because the measure, the input variable dollars, decreases by exactly 1 in every single step. Since the if-while is a natural number, it has to eventually reach 0, and the program halts. Total correctness achieved.
So once we have this non-destructive multiplication algorithm proven correct, we can move up a level of abstraction to exponentiation.
And here is where we see the advantage of modularity, even in this incredibly constrained system. Exponentiation is just repeated multiplication.
So we can use the multiplication algorithm we just proved, AMA-EOB, as a conceptual black box.
Exactly.
So when we prove the exponentiation algorithm, we're counting down the exponent, yayo, and in the body of the loop, instead of raw addition and juggling variables, we just drop in the entire validated multiplication logic structure, which we already trust.
Absolutely. The argument for correctness becomes hierarchical. We can rely on the correctness of now B. The only new thing we have to prove in the exponentiation algorithm is that its outer loop iterates the correct number of times and, critically, that it manages the data flow between the multiplication steps correctly.
Making sure the result of one multiplication becomes the input for the next.
Right. And this modularity is a foundational principle of all scalable software, even here at the theoretical level.
Okay, moving on to another fundamental operation that is deeply, deeply tricky when you are restricted to natural numbers, subtraction. We're analyzing the implementation of what's called cutoff subtraction, which is basically max xy.
Cutoff subtraction is necessary because we literally cannot represent a negative result. If the calculation yields a negative number, the result must be capped or cut off at 0. If 651 and 1 SOT, the answer must be 0, not 303 SO.
And the genuine elegance of the MiniPy solution lies entirely in exploiting the language's core semantic constraint to achieve this.
It's all about that one rule.
The rule governing decrements on 0.
Yes. MiniPy's formal definition dictates that when operating on a natural number variable, 0,1 equals as 5m. If a variable holds 0 and you try to decrement it, it just remains frozen at 0. This is the boundary condition we're going to program against.
Okay, so let's look at the implementation of sub x. The sources show that the code is almost ridiculously simple.
It is.
It's one loop that decrements both 60 and dollars at the same time, while y, 0x most 1, y most 1. That's the entire algorithm.
That's the entire program. Now let's see this constraint-based control flow in action. We can walk through the two possible cases.
Case 1, the easy one. 6.
Okay, let's say $16 and one $3. The loop condition is some dollars.
Which is true.
So they both decrement simultaneously. After 3 iterations, what happens?
Sits 0 and the loop terminates. And $6 has gone down by 3, so it's left holding 7.
The result is $10 and $3.70,000. Perfect standard subtraction.
Simple enough. Now for the interesting case, where standard subtraction will give you a negative number. Case 2, 6 y8rs and one $7. Say 6,033 and are $1.
Okay, they start decrementing together. After 3 iterations, $6 is now $0.
And it's now $7.
Ah, but it's still not 0?
It's still not 0, so the loop has to continue.
So on the 4th iteration, trial 7, we execute x equals 1, but $6 is already 0.
And because of that semantic constraint, $6 remains frozen at 0. It simply cannot store negative numbers.
Meanwhile, y just keeps on decrementing.
Right. $1 goes to 6, then a 5, all the way down. And $6 stays at 0 the whole time. Euler continues this path until it finally hits 0 and the loop terminates. And what's the resulting value of $6?
It's $0.
0.
That is stunning. We achieved the difference of $6 and we got 0 of $6. All of this without an explicit if-else statement, without a comparison operator, and without any complex branching logic.
This is where the theoretical definition of the language becomes the most powerful programming tool. The mathematical definition of the data type is the control flow. You are leveraging the boundary condition of the natural number system itself to perform branching logic. I find that to be one of the most intellectually satisfying tricks in this entire system. It truly shows that logic can be embedded in arithmetic.
It does.
And we can now use this simple building block, cutoff subtraction, to construct something even more powerful. The maximum function,
The function seems impossible at first, right? How can you possibly determine which of two numbers is larger without an if statement, without saying, if me is bigger than dollars?
Exactly. Comparison seems like an inherent necessity for finding the maximum value.
But we don't need comparison operators. We need a mathematical identity that inherently includes the logic of comparison. And the identity used here is max and m plus max in the $.
Let's break down that identity because it looks a bit abstract, but it's surprisingly intuitive when you realize the second term is just our newly built cutoff subtraction block.
Right. We have knowledge just sitting there, and we are adding the result of the cutoff subtraction of non-S dollars.
Yeah.
And that cutoff subtraction term will either return the positive difference between them or will return $0.
So let's trace this with the identity. Let's run the two cases to make sure it works.
Okay. Case 1. 1 in dollars. Let's say over $10 and was $3. The equation becomes 3 plus max n, the 3, $0.
Right, okay, so the max end row part evaluates to 10 and 3, 3 plus 7 days.
Right. We then calculate $3 plus 77. The result is $10. We correctly get math.
Perfect. Now, case 2. 1 in dollar, linear. Let's say 1 and 3, mm10.
The equation becomes number 10 plus max 3 $10.
And our cutoff subtraction implementation ensures that any result less than 0 becomes 0. So that whole term just yields $0.
Right. We then calculate $10 plus $1. The result is $10. We correctly got $1.
So, by composing two fundamental blocks, simple addition and our constraint leveraging cutoff subtraction, we have managed to perform advanced control flow. Specifically, case distinction, entirely mathematically. It's a profound proof that complex logic can be built from the most minimal arithmetic primitives.
It is the ultimate testament to the power of abstraction and mathematical reasoning in computer science.
Okay, so we've focused heavily on the programming tricks and the micro-level execution defined by the small step semantics, that little arrow. Now, let's zoom out to the underlying theory of the language definition itself. The big step semantics, represented by the double arrow.
The big step semantics represents a complete execution in one formal step. It says, starting in state A, the program eventually halts in final state B, assuming it halts at all. It abstracts away all the hundreds of small steps in between.
And we need this view when we want to discuss the fundamental global properties of the language itself.
Exactly.
And the first fundamental question posed by this framework is the language deterministic? That is, if I start the program with the exact same input state sigma every time, will I always get the exact same output result, assuming it terminates?
And the answer is unequivocally yes. MiniPy is purely deterministic.
Why is that guaranteed? I mean, in many real-world languages, especially with things like concurrency or hardware interactions, side effects can easily break determinism.
In MiniPy, the determinism comes down to the formal rules being disjoint.
What does disjoint mean here?
It means that for any given state, there is never a possibility of two different rules applying at the same time. There is never a choice in the execution path.
Oh, I see.
Look at the control structures. If the condition for a while loop or an if statement is true, only one path is taken. If it's false, only the other path is taken, or the loop terminates. The structure of the language is definitionally free of ambiguity.
Condition is either true or false. There's no maybe.
There is no maybe. So because the language rules are mutually exclusive, a given starting state can have at most one successor end state. This structural impossibility of ambiguity is what guarantees determinism.
So you can run the multiplication algorithm 1,000 times with 6 to 5 by and 1/100th three-lers, and you are guaranteed the result RI55 guys every single time, provided it halts.
Provided it halts. Which brings us back, frustratingly, to the second question. Is the language total? Does every computation always yield a result?
And the answer, as we established earlier, is the hard truth of computer science.
Remember,
No.
we have to keep revisiting the existence of that simple non-terminating loop, while x equals 0, x plus equals 1. That single possibility proves that MiniPy programs are not guaranteed to halt.
So the function is partial.
Therefore, the function computed by the language is, by definition, a partial function.
And it's important to differentiate this concept for you, the listener. This isn't just about a program crashing. This is about the function being mathematically undefined for that input.
Exactly. When the program runs forever, the big step semantics transition, that double arrow, simply doesn't exist for that input. If you try to map the input 6BL1 to an output state, the output state is simply missing. This is a fundamental, non-negotiable property of any computational system that allows general repetition or loops.
So to summarize the theoretical side, using the language of the sources, achieving total correctness for any specific MiniPy algorithm requires satisfying both of these theoretical pillars.
Absolutely. You have to prove totality, which means termination must be proven using that strictly decreasing natural number measure. And you must prove partial correctness, ensuring the result is mathematically right if it halts, which is proven using loop invariance.
And only those two proofs together guarantee reliability in this rigorous minimalist environment.
That's it.
And now, for the final, most advanced challenge. We have to tackle the constraints of having no stack when we need to iterate a complex process multiple times. The ultimate complex task in the system is functional iteration, or FN excess dollars. We want to execute a specific operation, let's call it $5, maybe a squaring function, exactly null times on the input value $6.
Hmm.
This is essential for algorithms ranging from financial modeling to cryptography.
Oh, absolutely. And in any modern language, you would define $5 as a subroutine or a function, and you'd call it either iteratively within a loop or recursively.
And the stack is the hero there.
The stack is the hero. It handles all the critical bookkeeping automatically, saving local variables, managing return addresses, ensuring the function execution context is totally isolated and cleaned for the next call.
But MiniPy offers us none of that infrastructure. No stack, no automatic context saving, no isolated scopes. So how on earth do we simulate this function pipeline?
The sources explain that defining a macro or a function in MiniPy is purely a conceptual construct. At the implementation level, it translates into raw text substitution.
You mean copy-paste?
Literally copy-pasting the entire code block for $5 into your main program, $CV, which is running the outer iteration loop.
That immediately raises the biggest red flag for a modern programmer, the danger of variable collision.
This is the critical constant danger. If the function $5 uses internal temporary variables, maybe variables named I or T for its own loops.
And your main program, G, also uses I or T for its outer loop control.
Running $5 will instantly overwrite and destroy the control variables of dollars. That collision completely invalidates the program state and breaks the required iteration count. The whole thing falls apart.
This is why the stack exists in the first place, to prevent this collision by giving every function call its own clean block of memory for its local variables. Without that, the MiniPy programmer is forced to manually manage all the context.
Indeed. The solution requires meticulous, manual variable mapping and assignment discipline. You define a structure where the outer loop is controlled by 9. Inside that loop, you insert the copy-pasted code of $5. But $5 has to be written with two very specific conventions.
Okay, what are they?
First, $5 must take its input from a designated input variable, let's say 6 hours. And second, it must place its result into a dedicated result variable, say 0 tossed.
And I'm guessing the variables inside F have to be unique.
Yes. Furthermore, the code for $5 must use variables that are entirely unique and known not to collide with the loop variables of your main program, D or dollars.
So every time $5 executes, the computation runs, and the newly transformed value sits safely in $0.
Right.
But to run the function again in the next iteration, that output has to become the next input.
Yes, and that's the crucial explicit step, that manual data transfer. Before the next iteration of the outer loop begins, we must execute the explicit assignment set of 0.
You're copying the output of the last run back into the input variable.
Manually updating the context for the subsequent run, yes.
Wait, think about the implication of that. You are manually managing the data flow that a compiler handles automatically in every other high-level language we use today. You are essentially implementing the function call convention, the parameter passing, and the context saving, all through carefully ordered assignment statements.
It's the ultimate demonstration of why high-level languages are so productive. They automate this incredibly painful and error-prone process. But the MiniPy constraint demonstrates that the functionality isn't magic. It's just a sequence of assignments and loops that has to be manually verified.
This is effectively a self-managed single-level function pipeline. The outer loop counter nuller ensures termination, while the manual copy operation ensures data continuity and avoids that deadly variable collision.
And as with all complex algorithms in this system, proving this structure works requires mathematical rigor. We can't rely on induction over a physical stack, because there isn't one.
So what do you do?
Instead, the proof relies on mathematical induction over nuller, the iteration count.
Walk us through that inductive proof strategy.
We use the assumption that the process works correctly for nuller steps. That's the inductive hypothesis. So we assume phenx produces the correct output.
Okay.
We then prove that one more execution of the copied function code, $5, followed by that absolutely necessary variable copy, $6 is out, correctly yields the result for 5n plus 1x.
And that proves it for all n.
This inductive proof demonstrates that the entire machinery holds together across any arbitrary number of steps. It proves that despite the constraints, the manual variable management is sufficient to handle complex iteration. MiniPy might look simple, but the complexity is pushed entirely onto the developer, demanding extreme precision in variable allocation and flow control.
MiniPy forces you to understand every single step the machine takes, because you are the one responsible for defining those steps perfectly. This deep dive into MiniPy has been a fascinating journey into the absolute foundations of computation. We've seen how programming elegance is really born out of severe constraint. Let's quickly recap the core conceptual lessons we learned from being forced to program under these conditions.
First, I think we learned about the necessary programming tricks. That variable juggling act required for non-destructive operations like multiplication.
Right.
We had to invent a manual temporary register, ETE, just to save and restore context that a CPU would normally handle via stack. This forces total discipline in managing your resources.
Second, we saw the incredible power of mathematical semantics. Cutoff subtraction showed us how the language's fundamental definition that $0, $1 on natural numbers could replace explicit if statements and complex branching logic.
The boundary conditions of the math are the control flow.
Exactly. And finally, we reinforced the theoretical importance of partial functions and the challenge of total correctness. The existence of that one simple, non-terminating loop proves that MiniPy is not total, and that termination must be proven alongside partial correctness for any reliable algorithm.
The ultimate conclusion from the sources is clear. Even with a language as dramatically simple as MiniPy, without true function calls, without true recursion, without a stack complex calculations like exponentiation and functional iteration are entirely possible.
Solely through carefully constructed loops and disciplined variable management.
And that means MiniPy is computationally complete. It's implicitly Turing complete. It can calculate anything that any modern computer can calculate.
Which leads to our final provocative thought for you to consider, because this is where the theory really hits reality. If MiniPy is deterministic and only requires sequential assignments and simple loops to achieve Turing completeness, what are we really paying for when we use modern high-level languages like Python or Java? Is it power, or is it just kindness?
The answer implied by this entire system is that modern languages don't give us more computational power. They give us abstraction, safety, and convenience.
They give us the features like true stack-based recursion and cleaner variable scoping that make code elegant, readable, and debuggable.
By automating away the kind of painful manual variable juggling we just spent this whole time detailing.
But fundamentally, the constraints of MiniPy force us to see the bare computational truth that's hiding underneath all that comforting syntax.
It's the core logic that underpins everything.
A huge thank you for sharing these sources with us. If you want to feel truly well-informed about the foundational logic that powers everything you do on a computer, diving into foundational computability like MiniPy is always the best place to start.
Absolutely. Keep diving deep.
We'll see you next time.